In this final chapter, we are looking at correlations and regressions. This is a pretty significant chapter, and I would almost argue it's almost the whole point of this course is this chapter. So here what we're trying to do is look at the relationships between variables and trying to determine if we can mathematize that relationship between the two, and then take from that as well whether there is a causal relationship. So remember, the difference between correlation and causation is that whereas in both cases they might move in the same direction or in opposing directions but to the same extent at the same time, what a causal relationship, it's a little bit deeper because it requires that it says something more about the relationship. It requires that one thing happen first and then the other thing happens. The best example I like to give for this difference between the two is the example that was given to me when I took statistics oh so long ago. And that's more people drown. There are more drownings and there's higher ice cream consumption. Now, with the way I set that up, we can already tell that there's probably not a causal relationship between the two, right? It just so happens that it both happens in the summer, and at least on the mainland, people swim more in the summer and they eat more ice cream. So we could say that those two variables are correlated, but that they're not causally related. But do you see, at least even from that example, the problems that could occur if we mistakenly implied that there was a causal relationship between the two? So what are we going to do here in this chapter? Again, we're going to review looking at a two-variable space. We're going to be looking at the relationships between those variables and calculating what's called a correlation coefficient to be able to talk about the degree of correlation, and then finish that up by talking about regressions and how a regression implies a bit more of a relationship between the two. Okay, so let's start. Sorry, I also print out the slides because that's how when I'm talking about them, I'm looking at them. I had not stapled them, so I'm sorry about that. Okay, so here we've got a linear relationship between the two that we've already stated here, that y equals 9x plus 3. So the idea here is that for every variable of x that we have, you would be able to compute the y, right, with simple algebra. And we can see that this is a linear relationship because basically every time we increase x by 1, it increases y by 9, right, because the slope factor here is 9. From this equation, we can see both the slope term, the 9, as well as the y-intercept, which in this case is 3. So basically, if we were to graph this out, oh yeah, it won't let me add, does it? Yeah, it does. Okay. So if we were to graph this out, it would be starting at 3, right, where that's y and that's x, with a slope of 9. Right, that's just my, whoa, yeah. Okay, sorry about that. It took it away. Okay, well, hopefully you saw what I did there. Sorry about that. Okay, So we have here just a general construction of how things look for a term. Now, if we start to create a scatter plot of data, right? So if we have a sample size of 12, and we get everyone's height and weight, or weight and height, X being weight, I'm presuming, Y being height in inches, I'm presuming, we could plot this data here. Now, what are we seeing here, right? We're seeing in general right, that things are generally moving in a positively correlated way, whereas Y is increasing and X is increasing. We don't really know the slope or anything like that, but in terms of the scatter plot, we can see that there is some relationship between the two. Not too surprising, right? Most people are relatively, just as it implies, most people are relatively balanced, I guess you could say, in terms of their weight and height. Yes, we have incredibly tall people. Yes, we have incredibly short people. And we have very tall people who are very skinny. We have very short people who are heavier in weight. We know this to be true, right, just in terms of the variety. But we know that for the most part, we follow this general relationship that the taller you are, the heavier you are. Okay. So, all that this slide is basically saying is that, yes, we can see that there's some relationship between the two. Now let's talk about how we would describe that relationship. Well, the way that we would describe that relationship is by calculating a correlation coefficient. What that correlation coefficient does for us, it tells us the degree of the difference between the two. We can calculate that R value here. There are also, I don't mean to imply that you have to know how to do it this way, because there are actually pretty good calculators online. Where you can simply put in the X values, put in the Y values, and then calculate the R. To be honest, this is how I do it. I'm a little too old to be. Long ago, when I was in your shoes, I learned how to calculate it, but I also learned it at a time when the calculation of this kind of thing was much more difficult. Let's see if it lets us do this here. So I'm just taking my values here. Oh, duh. This is trying to calculate a Pearson correlation coefficient. Yeah, we would need more variables. Sorry about that. Yes. We couldn't do the Pearson, but we should be able to do. Yeah. I think we can do it this way. Sorry, I'd have to fix all this. Sorry. Anyway, there are I don't want to belabor this here, but there are calculators out there, and I'm not expecting that you're going to follow these equations. Just be aware that it exists. Okay. What can we say about this correlation coefficient? That it is either going to be, it's between -1 and 1. So obviously there's a positive sign in front of the 1. If it's 0, then that would mean that there is really no relationship. So that's what's implying here in absolute value terms. In absolute value terms, if it's closer to 1, or if you took away the absolute values, if it's close to 1 or to -1, then we know that we have a pretty strong relationship. If it's negative, then there'd be an inverse relationship. If it's positive, then there would be a direct relationship between the two. And that's what you see here. If one is decreasing as the other increases, again, that's what we call an inverse relationship. And then if they're both changing in the same direction, that would be what we call a direct relationship between the two. Again, not implying causality, just saying that this is how they are moving with each other. Okay, so here's again that same data. It's just giving it to us in this format. Yes, I mean, I'm not disputing the fact that you can go through this here and go through this here. But let's try to make sure we can do it here. Sorry. Okay, I'll pause this. Okay, so all that I did here while I had this pause is I just fixed the data. So I recopied and pasted the data here, and I just had to separate it out by comma. And you can see the calculated coefficient for our sample size of 12. 0.8684. 0.868, and presumably there's a 4. I'm not asking you to do all these calculations, and quite frankly, I care less that you're able to calculate it than that you know what to do. Which would be, I just went onto the internet and I just typed in correlation coefficient calculator, put in the data here, and it plotted it out here, and gave me the data that I need to do. It even shows you the calculations. So on the off chance, I'm not going to ask you to do it, but on the off chance someone asks you to show your work, you can do that right here. This is what computers are made to do. And there's no need to there's no need to replicate that in any way. Okay. And you can see it calculates all the other things here for us as well. Okay. Let's go back to our slides here. Now, what if we want to start to create, look at this from a regression perspective? Then what that would mean is that we still have our fixed points. Like in this case, right, this is when it looked like y equals 9x plus 3 plus some error term, some degree of randomness. So we have a regression line, and we have some way in which there are random deviations between it. That those random variables, that random variable is normally distributed, and we're generally expecting that that mean value of the randomness variable is 0. In this case here, we know that because of the way that the regression is constructed, that there's a direct relationship between the two. We know that because there's a positive sign right here. And again, we have that error term, that random variable. And essentially what it does is it takes, right, we can basically then plot that line, but then you see a normally distributed error term around it, allowing the points to deviate from the regression line by the error term. Or in some sense, our variance here, our standard deviation squared. And we can calculate what's known as a sum of squares to determine how well does that data fit. How well does that data fit? We could also call this our square term. How would that be constructed? Well, essentially what we would do is take the sum of the error terms and square that. Again, I'm not too interested in the mathematical construction of this, as long as you are comfortable with the calculation of it otherwise. What that means for us here is I can go back to our calculator here. Well, it actually gives us a lot of, again, I'm just a random. Where if we had our values here, we could plug in those values and we could get our, the x and y variables, we could get our linear regression equation. And with that, I wonder if they're going to, let's see here. Sorry. So let's just do this. Okay, I'll pause this so I can do this and then you can. Okay, I'm back here. Again, I'm not as worried. I think there are certain instructors who care more that you can manually calculate this, but in the real world, I can't imagine that you would be. All I did is I just copied and pasted the x and y values here into our linear regression calculator, I don't know, from statskingdom.com. And it got me my residual values, basically my error term, my predicted value from the regression equation, and then it gave me basically my alpha term and my beta term, and gave us our squared. It gives us all the variables I would ever ask you for, certainly on the exam. You know, what am I trying to do here? What am I trying to say? I'm trying to say, again, what is this introductory statistics course supposed to do? It's supposed to give you some familiarity and reduce any of the stress you feel when you encounter a statistical question. Some instructors will add on to that you need to be responsible for calculating everything. I don't think that necessarily needs to be the case. I did it once, I did it at one time in my life, and I'm not sure what I personally got from that. And so in some sense, I'm just replicating that here. There are much better websites out there than when I was doing this. And if I put those x and y values here, I get all the same data that I need. Okay, let's go back to the slides here. And so you see this all here. I mean, you don't need to prepare the data, obviously, because it's already prepared for you. But it gives you the exact same things here. The only thing they're doing here is they're just switching the terms here. Putting our x value in front. Minus 0.125. Right here. Okay, so generally, one thing that a regression then would allow you to do is it would allow you to make forecasts, talk about data points that you didn't actually see, but allow us we can make an educated guess about what those values can be. We are at this point then extrapolating if we're dealing with data that's outside of the range of the XY values that we had right here. So we could make some errors, and we should note that for others, because it's not standard practice that you will extrapolate. In general, you're supposed to use a regression to predict values within the range of values you've already collected. We have our sum of squared errors here, but this tells us that data that we need here. We have our sum of squares right here. It calculates it for us, so I'm not too concerned about you being able to do it, as long as you know what you're looking for here. And it gives us the actual calculations here. It's actually a pretty good website. Wasn't familiar with it before I started this lecture, but it's pretty sufficient for what you need to do here. It's statskingdom.com. Now, what we can do is transition to talking about this in terms of a confidence interval for that slope term. So, because of the size of the sample, we're going to have to do this with a t-statistic. But calculating the confidence interval is no different than what we've already done before. And again, we can construct a null and alternative hypothesis depending on what we're looking for. I don't think this is gonna, well, I suppose, it does. You'd have to put in the data here to calculate this out for us here. Just I don't think it's going to provide us with the data for the it's not going to give us anything here. So we do see, in terms of the goodness of fit, it does give us a little bit of a description here that probably from the for this two-tailed test, for the null hypothesis at the 5% range, it does give us an idea that we would reject the null hypothesis. So actually this site does tell us what we're working with here. So I'd strongly suggest you use this site when it comes to the homework and the exam, because this actually should tell us mostly what we're working with here. You would see on that site, on the website, but also then here, we would test the value of both the y-intercept as well as the slope term. And you saw this here, y-intercept as well as the slope term. And then our final thing here would be, again, looking at our coefficient of determination. Again, just as we did before here, yes, you can calculate a thing, but we can also get these values from this site. So I'm not just trying to be practically oriented here, but in some sense, when you start talking about regressions, people get very worried. And if anything, I'm trying to encourage you to at least use some of the websites out there. And I just kind of happened upon this Stats Kingdom one, but it actually does cover most of the material we're doing here, because we can get now this confidence interval. and we can see that we can calculate our residual outliers, and we can use that to construct our confidence interval, which we have right here. So, this, I mean, I know this is short, it's only 30 minutes here, but again, I'm going to use the same philosophy of, we now have a sense of how to approach a regression and why it's important, and then we're going to look at the problems, and I'm going to walk you through various ways in which we can apply these theoretical concepts to the problems that we're presented.